Welcome all. In continuation of previous lecture on distillation, today we are discussing vapor liquid equilibrium or VLE diagram. Now, separation of binary or multi-component liquid solution having differing boiling points by distillation is achieved by the attainment of equilibrium between two phases involved in this operation. One phase is liquid phase, another phase is vapor phase. Now the distribution of components in these two phases is governed by the vapor liquid equilibrium or VLE. VLE data helps to relate the composition of a liquid phase to the corresponding composition of the equilibrium vapor phase at a particular pressure and temperature. Let we assume a simple binary system consisting of component A and component B. Component A is the more volatile component. Significance: its boiling point is lower than component B and vapor pressure is greater than component B. On the other hand, component B is termed as less volatile component. Now, this equilibrium data may be represented as an equilibrium diagram in different ways. TXY diagram, where T represents the operating distillation temperature, X represents mole fraction of more volatile component A in liquid phase, Y represents the mole fraction of component more volatile component A in the vapor phase at equilibrium condition. It is also known as constant pressure VLE diagram. Second type is PXY diagram, where P represents the operating pressure. It is also known as constant temperature VLE diagram. We also make plot only XY diagram. Another type is HXY diagram, where H represents the enthalpy, X and Y represents mole fraction of component A in liquid phase and equilibrium vapor phase. Today we will discuss the first type, that is TXY plot or constant pressure binary VLE diagram. So based on our assumption, the more volatile component A and less volatile component B compositions are presented in the x-axis and the corresponding temperature is presented in y-axis. As x represents the composition of A, 1 minus x represents the composition of B in the liquid phase, and y represents the composition of A in vapor phase. So 1 minus y represents the composition of B in the vapor phase. Because it is a binary system, so sum of mole fraction of both components equals to 1 in both the phases. Now in this diagram, the lower red curve represents or termed bubble point curve or TX plot or saturated liquid line, and the upper curve is termed as dew point curve or TY curve or saturated vapor line. From this curve we can explain the nature of the mixture, the relation between liquid composition and corresponding equilibrium vapor composition for a given temperature and constant pressure P. Now the points on the lower curve CRUN, they represent saturated liquid composition. On the other hand, points like E, Q, V, Z lies on the upper curve represent equilibrium composition of A in a saturated vapor. So lower curve represents the composition of saturated liquid and the upper curve represents the composition of saturated vapor. Now if we join C and E by a straight line, it will indicate the composition of saturated liquid at a particular temperature and corresponding saturated vapor composition, which is represented by E. And this line CE is known as tie line because it represents equilibrium liquid vapor composition of A at a particular temperature and constant pressure. By point C lies in the saturated liquid phase and E lies in the saturated vapor phase. An infinite number of such lines can be drawn in the diagram. Now the region below the bubble point curve or TX plot represents only liquid phase, that is single liquid phase. That means no presence of vapor. It is known as subcooled liquid. On the other hand, region above the upper curve is indicated the presence of single vapor phase, which is known as superheated vapor region. Now the region enclosed by the bubble point curve and dew point curve represents the two-phase region or liquid vapor mixture at equilibrium at a constant temperature and pressure. Now the bubble point curve and the dew point curve meets at point A and point B, where A represents the pure more volatile component, B represents pure less volatile component. And TA indicate the boiling point of A, TB indicate the boiling point of B, and we know that as A is more volatile, its boiling point is less than the boiling point of B, pure B, which is less volatile. And that is the reason TB is located in the above the TA point. Now the point S. Point S inside the enclosed region represents the coexistence of a liquid vapor mixture at equilibrium on the tie line C. Point S is a liquid vapor mixture at equilibrium which consists of a saturated liquid phase with composition of A denoted by X at point C and a saturated vapor phase at equilibrium with component having composition denoted by capital E. Now the portion of A in saturated liquid and equilibrium saturated vapor phase is such that the mixture composition of A lies at S. Now the relative amount of equilibrium liquid and vapor phases can be related by the two segments of the tie line following the inverse arm rule. Moles of C divided by moles of P equals to line segment AC divided by line segment CS. So it is calculated following the inverse arm rule. Now let's consider a subcooled binary liquid solution of composition indicated at M in a closed vessel at a constant pressure say P and heating is started. Initially, the liquid temperature rises without any vaporization until it reaches the point R, which lie on the saturated liquid line, following the line MR, which is vertical, which is a vertical line. At point R, the first bubble of vapor will form, having a composition at Q, which is richer in more volatile component A. Hence, the lower curve is called bubble point curve because along this lower red curve, any subcooled liquid when heated up, first bubble of vapor is formed. Now on further heating, the temperature of the solution rises following the line RO. On heating, the saturated liquid line shifted from R towards N, following the line RUN. Since with the continuation of vaporization, the more volatile part in the residual liquid mixture decreases gradually and the boiling point of the remaining solution continues to rise. Now say at U, the corresponding vapor composition of A is indicated by V. The vapor composition in terms of more volatile also decreases than Q as less volatile part increases in the vapor phase with progress of time. In this way, as heating continues, more and more vapor forms at the expense of liquid. When the last drop of liquid of composition N vaporizes, a saturated vapor mixture is formed at Z, which has the same composition of more volatile component A as the initial liquid solution denoted by point M. On further heating, from Z to O, vapor is being superheated without changing any composition, and this vapor is called superheated vapor because no phase change occurs, the total liquid already vaporized. It is observed that on heating, the solution vaporization occurs over a range of temperatures between R, that is the bubble point, and Z, that denotes the dew point. This temperature range is known as the boiling range. In case of pure liquid, there is a fixed boiling point at a particular pressure. But boiling point of a solution has no meaning. The boiling range of a liquid solution is more appropriate terminology and it varies between the boiling bubble point and the dew point. Now, if saturated vapor at O is started to cool at constant pressure, it will follow the same path OM in the reverse direction. On cooling from O to J, no condensation takes place. Only vapor temperature drops. Condensation of vapor first starts at point Z on the upper curve and the first drop of liquid, that is called dew, forms. Hence the upper curve is known as dew point curve. On further cooling, the vapor composition will change along the ZQ line and the first drop of dew that will form, it has a composition denoted by point N. On cooling, the vapor composition will change along the ZQ line in the upper curve. When the entire vapor will be condensed, the saturated liquid solution of composition P will be produced. On further cooling, we may obtain a subcooled liquid of the same composition at N. So from this discussion, it is clear to us this TXY plot gives us an idea that on vaporization of a solution, binary solution, in the vapor phase, always more volatile component mole fraction generated at equilibrium is higher than corresponding more volatile component composition in liquid phase. All the tie lines indicate the same. The composition of A in saturated liquid in C is less than corresponding saturated vapor composition indicated by point E. Similarly, saturated liquid composition at R for A is lower than the saturated vapor composition of A denoted by Q. And why the lower curve is called bubble point and upper curve is called dew point, it is also clear to us. Now the equilibrium vapor liquid data, XY data, that is XY data, is a very useful plot in distillation calculations. It can be drawn from the TXY plot as shown in the diagram, or by noting the values of X and Y following the tie line. If we follow along the tie line, we have to draw X versus Y data where Y is plotted along the Y axis, X is plotted along the X axis, and the X equals to line is denoted by the diagonal. Now from every tie line, if we draw the vertical lines like the blue line, orange color line and the green line as shown, and then we to the diagonal line and then we draw the horizontal lines, we get few points which indicate the locus of the equilibrium XY diagram. Since more volatile, mole fraction of more volatile A is more in the vapor phase than corresponding equilibrium composition of it in the liquid phase, equilibrium XY line always lies above the diagonal line X equals to Y. It has a significance which says that if the distance between the diagonal and the equilibrium XY line is more, separation by distillation is very easier. So today we discuss in detail the TXY diagram